other things now, the other realm of science, of what I would call the postdictive as opposed to predictive, post after as opposed to pre before. Postdictive sciences, under that I include medical science, clinical medical trials of drugs, social science, data science, and associated with data science, what's now called machine learning. In this postdictive science, as opposed to predictive, we can also call this deductive science. We don't have strict laws of nature that we use to make predictions. And I'll say as a physicist that in some sense that means that these are weaker sciences than physics. And yet at the same time, it's because it's so much harder in these areas to formulate fundamental laws that they're weaker. So physics is more successful because, honestly, it's simpler to formulate laws for atoms and black holes and everything in between than for people and societies. But in this postdictive or deductive form of science, we don't have predictions beforehand. We just collect data. We collect different types of data, and we see if there's discernible connections between different variables or different pieces of data without trying to predict them beforehand or prove there's a causal relationship. You go on internet forums, you go on Reddit, every time there's a scientific or medical study, people will say, well, correlation doesn't prove causation. Well, usually when you go back and read the actual study, the researchers didn't claim that. But anyway, in this type of science, you may want to, for example, know if smoking is correlated with cancer. So what's done is to take some data that is, in the simplest case, just a bunch of people. Do they smoke or not? And did they get cancer or not? Of course, this is the absolute simplest case. And in general, it's much more complicated because you could get cancer due to many different variables. What if there's other things, of course, as we know by now, besides cigarettes that cause cancer, as well as many other causes that we're not aware of? There's so many other things that you have to find ways to eliminate their influence. Generally, the term is you need to control for those variables. So we'll say smoking causes cancer, already controlling for other areas of health, etc., etc. And of course, again, this is the simplest case of deductive science where you take two pieces of data and see if there's a connection between them, but it's generally a lot more complicated because you want to make sure the connection is genuinely between those pieces of data and not some other random influence that came into your experiment, or that they're due to some other random effect that you happen to pick out from your sample of people that they all happen to have this same random effect. And so part of this postdictive or deductive science is called statistical hypothesis testing. And it's a way of ensuring that you've eliminated the influence of other variables and ensuring that your result or your connection between the variables is genuine and not by chance. But of course, as you can see, it's not predictive. And so because of that, it's a lot weaker than something like Halley's Comet because you didn't predict it beforehand and know what you were going to get and then confirm it. You checked to see if two things were related. You tried to eliminate other random causes that may make them appear to be related, but still it's obviously a much stronger result in a predictive science. Sometimes people talk about maybe a physics experiment and say, what was the sample size? Sample size is something that comes into clinical studies or deductive science. A bigger sample size and you have a lower chance that pure randomness could result in an apparent connection between pieces of information that are in fact unconnected. That's what p-score measures. P-score is the likelihood that an apparent connection is due to pure randomness. Well, the concept of sample size doesn't apply in an experiment like the one for Halley's Comet or for the ball rolling, because you're not just doing a random test and comparing different pieces of information. You're making a prediction beforehand. Every point on the graph of where Halley's Comet is as a function of time, even if it's 1,000 or 1,000,000 points that you measure, is another sample in a physics experiment. And that's why physical science is generally much more powerful than this postdictive science. A related issue is, what about how in medical studies we often hear a lot about how researchers don't effectively eliminate the random or spurious connections that make things appear to be linked when in fact they're genuinely not. And so that's why you hear about one day coffee is good for you and the next day not good for you. because it just so happens that these random apparent links do arise in experiments. And then a different random link arises in another experiment. And so this has caused a lot of confusion in science, and it leads scientists to say, well, we need to be more careful about replicating science. This is also the case in social science, where you can have contradictory studies, so people want to replicate. Replicability is a fundamental part of the scientific method, including in physical science and physics. You want to know that every single time you do this experiment, you get the same result. But this worry that, oh, should I drink coffee or not drink coffee? Oh, is this social science study correct or not correct? Do I need to send my kids to this school or not send them to this school? That's really not the same issue we encounter in physics, because in physical science, physics, chemistry, biology, the results of the experiments are oftentimes so deeply tied into the technology that we use every day. You could say, for example, what's the replication of Newton's laws, the proof of Newton's universal law of gravity? Well, of course, it has been tested thousands of times in many different permutations of experiment. But just to get one obvious example, the fact that satellites orbiting Earth, controlling your GPS and your communication signals, the fact that they don't fall out of the sky, every single moment that they fail to fall out of the sky and move on course, every single moment is a replication or confirmation of Newton's and, in fact, also Einstein's theories of gravity. And in fact, there was a replicability crisis in cloning studies, like cloning animals in South Korea, but it wasn't much of a crisis. A researcher, Hwang Woo-suk, claimed he was able to do something that he wasn't able to do. People tried it, they couldn't do it, and he was quickly found out. So when we hear about problems with replication, we worry, oh, do we really know what we think we know? You don't necessarily have to get so worried and concerned with the postmodern condition that everything we think we know is really false when it's something real science or not. In real predictive science, a lot of things are ultimately tied to everyday technology that we couldn't use, and we couldn't use for so long, thinking that something was right when it wasn't, or vice versa. Now, finally, we come to data science, which is the new big buzzword today. And what that really is taking this postdictive or deductive science and bringing it to the next level of intricacy due to the availability of much more data and much more powerful computers in recent years. You know, Einstein said that science is merely a refinement of everyday thinking. And what he meant by that was everyday thinking is using observation combined with logic to make predictions. For example, you know when the bus comes, you know that the bus takes longer when it rains. You can make a prediction if you need to leave a little bit earlier to get to work on time when it's raining, and so on and so forth. And in science, all we do is take that process and refine it and put the predictions in our experimental knowledge, like the bus coming late, and us needing to leave a little bit earlier, and put them in much more precise quantitative terms. So today, data science, this new buzzword associated also with machine learning, is just a refinement of the standard type of deductive, postdictive science that is used in clinical medical studies and social science. Because what's done now, the seminal example of postdictive science is I take two variables, I plot them, and I see if I can draw a line through them. That's linear regression, simple linear regression. Well, in data science, what we do is we take massive numbers of massive pieces of data, and we don't just compare one thing to the other. We may take, say, 100 variables and record them 1,000,000 different times, and from those 1,000,000 examples of 100 pieces of data, see if we can deduce a link to some other piece of data. So that's certainly much more complicated than drawing a line through a bunch of points on a 2D graph. You have a 100-dimensional space with 1,000,000 points, and you want to find some connection between them. And then the techniques that are used in order to link those to those pieces of information to the other pieces of information, to draw the line through the points, so to speak, are much more advanced. And essentially what the process is to use what's called machine learning, which is to try to combine different techniques to link all the variables together. But because there's an infinite number of different ways that you can combine those variables in order to output a predictive answer, you have to do what's called hyperparameters or hypertweaking. And that is, in the linear regression example, all you can do is tweak the angle of the regression line that you use, or possibly the y-intercept. Here you tweak the very methods that you are using and then systematize it with a computer. You get a computer to systematically go through many different methods of combining the data with many different tweaks and parameters to find the best way to make a connection that you're looking for. And that's why it's called machine learning, because it's a systematized way of having the computer figure it out for you. And it wasn't relevant before we had massive amounts of data acquired very easily, and it wasn't possible until we had more powerful computers that could do machine learning. So to recap, I divided science into predictive and inductive versus postdictive and deductive. Physics is the king of science, followed by chemistry and biology. In the postdictive or deductive science, we have clinical medical trials, social science, and data science.